Good evening, everyone. I'm Luis Jou Garcia from Keio University, master third year student in ITO group, and I'm going to present you my work about amorphization of semiconductors. First of all, let's see what is this of amorphization. This is an example of how a material, silicon, amorphizes when we implant an atom. As you can see, the main atoms follow this way, and secondary projectiles recoil and produce extra damage. So finally, we have here the dopant atom, some heavy damaged areas, and some light damaged areas. So after this, I want to start my presentation. First, a brief introduction about the basics, what I'm going to talk, then my experiments, and finally what I'm going to do after today. So let's start with the introduction. What is amorphization? So the word of amorphization says us everything. Morph means shape. So this is the diamond lattice. Means without. So when we lose the shape, we have amorphous material. And ation is just process. Why we need to amorphize the material? Because when we implant, we produce damage. And if the damage is not enough for amorphization, we are not able to make all the damage disappear by annealing. It's very hard. With amorphization, we got recrystallization at relatively low temperatures. And so we can ride out of most of the damage. And how is the damage produced? So there is a theory that says that when from 20 to 25% of the atoms are recoiled out of their lattice position, then the material behaves as amorphous. So it loses the properties of crystalline, and it becomes amorphous. How looks 20% of atoms recoil? You can see it here. Here the pink atoms are 20%. So you can see it if you want. And a nice theory to explain this is that when one atom recoils, 4 bonds are being destroyed. Therefore, one of every remaining atom loses 1 bond. So when all atoms of the existing lattice have lost 1 bond, the material stops behaving as amorphous. Now I'm going to talk to you about the simulator I have been using. It's Ion Implant Simulator from University of Valladolid. It's a binary collision simulator. However, it uses some molecular dynamics techniques to take parameters to improve binary collision, and also it uses Monte Carlo techniques mainly for decide the place of implant. So it covers a wide range of simulators. And the good point about this simulator is that there are two parameters that you can, and with that 2 parameters you can control almost all the implant process. One of them is the stopping power that defines how much energy is lost due to electronic stopping. The other component of losses of energy is due to recoiling. So there are many theories to define this energy. One of them is non-local losses. That is that the atom is stopped just because of the bulk. It's considered an homogeneous bulk. The local losses, or Owen Robinson, that the losses depends on how close the atom passes, the projectile passes through every atom, next to every atom. But in IIS, Ion Implant Simulator, it's used Brown-Kitagawa theory, that is more molecular dynamics from the point of view that the losses of energy depends of all the way that the atom of silicon, that the projectile atom passes inside the silicon, and it uses just one parameter, Rs, that is the radius of Wigner sphere. That is something like how much background charge does the projectile atom sees. This parameter changes for every combination of implanted dopant and bulk material, silicon or germanium, for example. And when we increase that parameter, we can see this effect on the dopant profile. So it goes deeper and also it's wider. The second parameter is the survival factor that helps us to determine how much damage is generated. It's just a factor. So with this factor, as you will see later, we can model some effects of dose, temperature, and so on. By increasing the survival factor, we make the damage profile. This is not dopant profile, this is damage profile. We make it increase and also get wider. So now I'm going to talk about the experiments. My procedure of experiments was obtaining experimental data from this group members or from some papers, some theory, make simulations, and trying to adjust the parameters of simulators to fit the experimental data with the simulated one. And finally, analyze results. And that's what I'm going to show you now. First of all, how depends the amorphization on some parameter called threshold. Threshold, this name is because it used to be a threshold, but now it's no more a threshold. They redefine, and it's just the maximum amorphizable, the maximum damage. So as you can see, when we decrease that maximum damage, the amount of amorphization becomes higher. Just because if we have our limit lower, it's more easy to reach that limit, so get 100% of amorphization. Finally, I have used as threshold value, in the case of silicon, 5 to the 22nd, because it's the atomic density of silicon, and in the case of germanium, 4.4 to the 22nd. I consider that the maximum damage should be the atomic density. So there should exist different degrees of damage, because maybe we are not able to see through XTEM all the damage, but if there are some non-amorphous areas inside the bulk, that might be the origin of undesired recrystallization and therefore some kind of category 4 defects in the boundary of regrowth. Then how the profile depends on stopping power. So as you can see, when we increase the stopping power, the profile becomes wider, and also the peak moves to the right and down. So this parameter depends for every combination of implant species and bulk material. In the case of arsenic in silicon, the best fitting value is the purple line. It's very close to the black line. That is 5, value of 5. As I said, larger parameter means larger Wigner sphere radius. It's something like the space occupied for each electron on the background. Then how the amorphization profile and dopant profile depends on survival factor. If we increase the survival factor, obviously the amorphization will increase, because we are letting more defects to survive. And an important thing is that the dopant profile is almost independent on varying the on the survival factor. This is good because this allows us to change the amorphous profile without modifying the already fit dopant profile. And now, how amorphization and profile depends on temperature. Okay, this is just due to implantation, not due to annealing. However, this is just due to implantation. That's why at such high temperatures we cannot see annealing there. So when an atom has thermal energy, it's more easy to go back to their position after being recoiled. So when we increase the temperature, the amorphization becomes lower. You can see here and this area how from 77 Kelvin to this point, for example, that is 1500 Kelvin, the amorphization varies in something like 10 nanometers. That is about 10% of the total width. So the implant temperature is something important to determine the AC, amorphous crystalline interface. What about the displacement energy? This is a parameter that has been traditionally used to explain the recoiling of atoms. However, in the literature we can find very wide range of values from 10 to 30 electron volts. And so that's why in simulator they usually we can see a wide range. And I made some simulation with 15 and 30, and as you can see, the amorphous profile doesn't vary very much, maybe just 2 or 3 nanometers. That's why usually in simulator is taking the value of 15 electron volts as recoiling energy. This seems to be no natural, no obvious. However, we should know that displacement energy is not a constant. It varies depending on the angle. It varies depending on the already existing damage. So for simulator that has a constant, that only you can determine a constant recoiling energy, it's best to use just one value. Then for the next slides, I'm going to use this graph. This is from Masera and Rosognil paper. And they made implants at different temperatures from 82 Kelvin to room temperature with two different energies of implantation, 150 and 300, and at different doses. And they saw how much amorphization they got. For example, for 3 to the 14 dose, they got amorphization between something like 80 and 200 nanometers. So I did this same simulation and I tried to adjust the surviving factor in order to fit it. This is the surviving factors, different surviving factors I tried, and this is the final result. So in this case, I got something like 0.5 is the logarithmic scale as surviving factor. I also did the same for germanium experiments from Yoko. And the first thing I saw is that the behavior of silicon and germanium by varying the survival factor is different. In silicon, you can see how material amorphizes fast, and then it doesn't vary so much as germanium. In the case of germanium, you reach the amorphization point usually lower, and it's easier to increase, and it's V-shaped. So it's like germanium is always more predisposed to be amorphized than silicon. Okay, now for every of the previous points, this 0.5, I plotted them. So this is the survival factor plotting depending on dose, and each curve is a different energy and temperature. Red is high energy and blue is low energy. There are two main things you can see. First, at low temperatures, you need more surviving factor. You need more defects survive. That is because thermal energy is slow enough to not allow the already recoiled atoms to go back to their original position. because at high energies that doesn't happen. We don't need to generate extra damage through surviving factor, even we are at higher doses, so it is expected more and more damage to be created. In the case of germanium, you can see similar trend, but I have not too much experimental data, so I cannot I have just that 2 lines, but you can see how the high temperature is beneath the high temperature, and also the trend of more recombination factor as you increase the dose. Also, in the case of germanium, the values are always higher than in the case of silicon. That also explain why germanium is more easily amorphizable. This is what I did here was see what is the width of amorphous region depending on the dose. And as you can see, when we reach some point, the amorphous region in this between 0 and 1 means that it grows very slow with increasing dose. The point where amorphous region stabilizes is higher in terms of dose for high temperatures. This means this is because at low temperatures, damage it remains there. Damage is not annihilated. It is also higher that point for germanium, but these graphs are not directly comparable because they are at different energies. Oh no, here is not germanium, sorry. In the case of germanium, it's different energies. So the point is that at low temperature, at low implant energies, the point is also more to the right side. How the damage depends on the amount of energy injected. What is this of energy injected? The energy injected is the total amount of energy that we have introduced. So it's the number of ions multiplied by their energy, and just this is a correction factor to show this in joules instead of electron volt, because it was millions of thousands of electron volts. So I did this because in this graph, comparing how much damage, the percentage of damage inside amorphous region, so just counting this area divided by this area, it seems to be at for a given dose at higher temperatures, this point, the amorphous region, the percentage of amorphization is lower. And also for high energies, the percentage of amorphization is lower. Why? Because if we have more energy, it is supposed to create more damage. Here, I plotted the injected energy in the x-axis, and here the amount of that injected energy that goes to each recoiled atom. So in the case of high energies, it's more easy. It's more easy to amorphize because there is less in. You give is needed less in average energy in electron volts to recoil each atom. So it is. I have not clear the differences between why this is. In this case, you got less amorphization. However, is needed less energy to recoil an atom. This is just an average energy, including all the effects. So this needed further studies, but I think it might be an interesting effect. These are the conclusions. They are just the copy and paste from all the green squares from each slide, so you can check it. I have been explaining that. And finally, about the future, what I want. I want to further study the amorphization and recrystallization and keep learning simulators. I'm going to Spain in February, and I will go to University of Valladolid to receive some lectures on their simulations. And also I want to try some modelization, so explain the physical meaning of the already seen effects. Moreover, this is from the results of quantitative evaluation of the amorphization depending on displacement of atoms got by Shimizu-san and Kawamura-san. I want to take that experiment values, try to fit with simulations, and got a model. So they stop being just a number, just a physical, just a experiment result, and I can got the physical meaning of that effect. And I think that's everything. Thank you very much for your attention.